to my YouTube channel. All right, Chemistry 1411. We're still dealing with Chapter 17, and we're going to take a look at Section 17.2, which deals with a standard galvanic, or what's sometimes called a voltaic cell. And you can see that the word volt comes from the name or the surname of Alessandro Volta, and we're going to be generating some energy, and we can measure energy as or electrical current can be measured in volts. So what is a galvanic cell? Well, it says that an electrochemical cell is an apparatus, and we're going to look at how to set up this type of apparatus for generating electricity just by using redox reactions like we looked at during the last class, and also you would have seen those in General Chemistry 1. We call these electrochemical cells galvanic cells sometimes we call them voltaic cells. Anyhow, we've already taken a good hard look at redox reactions, and we saw that a redox reaction is a reaction where electrons are transferred, right? Something gets oxidized, something gets reduced, and through that process, electrons are transferred. But what we want to do now is we want to harness the flow of those electrons to be able to produce electricity so that we could do some work. That's what you're doing when you use a battery. So let's take a look at the reaction, the redox reaction between zinc and copper 2+, which we could produce from copper 2 sulfate. So here we have a complete molecular equation, and then here we have the net ionic equation. So we're just going to focus on the net ionic equation, and very quickly we can see that zinc is undergoing oxidation and the copper 2 is undergoing reduction. So let's take a look at that. And what would happen if we were to take a bar of zinc and simply submerge it in a solution of copper 2 sulfate? Well, we do get this redox reaction occurring where the zinc is going to get oxidized, right? It's going to lose electrons. So the zinc is losing 2 electrons. And as the zinc loses its electrons, we produce zinc 2+ ions. But we only have a certain amount of sulfate ions in the solution. And so as the zinc loses electrons, okay, so we lose the 2 electrons, we form zinc 2+ ions. Well, the copper 2+ ions that are in here are going to take the 2 electrons to form solid copper, which is going to build up on the zinc rod. So there was a flow of electrons. That's why we can see the crust of copper building up on the zinc rod. However, we are not able to harness the flow of electrons when we do this experiment. So what's the solution? The solution is going to be that we're going to separate the 2 half reactions, and we're going to allow the flow of electrons to occur through a wire. And so we can measure the voltage, which again is a measurement of the flow of electrons. Let's take a look at how we would do that. I know there's a lot of text on here, but see if you can just follow along with me. If I was to take a zinc bar, okay, here I just have some pure zinc, and I put it in a solution of zinc 2 sulfate, and the concentration of that solution just happens to be a 1 molar solution. Well, we know that there's going to be a spontaneous reaction between zinc and copper 2+ ions, don't we? We know that from the last slide. Well, if I take a copper bar and I submerge it in a solution of copper 2 sulfate with a concentration of 1 molar, what's going to happen is that the zinc is the solid zinc is going to be oxidized. It's going to lose electrons. And so the solid zinc is going to produce electrons, which are going to go up the wire, okay? And it's going to produce zinc 2+ cations in here. So what's going to happen is as the electrons, and I'll just say it's 2 electrons because it's 2 electrons that are flowing, as the electrons flow through the copper and they come into the solution, what are they going to do? The 2 electrons are going to react with the copper 2+, right? Copper 2+ plus the 2 electrons is going to give me solid copper. And that's what you see is happening here, right? The copper 2 ions are being reduced to copper, and in turn, my solid zinc bar is going to get oxidized into zinc 2+ ions. Well, if you're if you're very astute, you probably noticed there's a big problem with this, isn't there? Right? If I start just generating random zinc 2+ cations here, and if I start decreasing the concentration of copper 2+ here, that means I'm going to have a buildup of negative charge on this side, and I'm going to have a buildup of positive charge on this side. So that means we've got to have a way to balance out that excess charges that are being formed. And the way that we do that is we use what's called a salt bridge. A salt bridge is nothing more than just a U-tube made out of glass, and that's what this is right here. It's just a U-tube, not a YouTube like the channel or the website. It's just a U-tube, and it's filled with a solution of something like potassium chloride. We usually use something that's an inert salt, and we invert that U-tube into the two beakers containing our solutions. And so on this side, this side over here, I told you that we would have a buildup of positive charges. And so if we have potassium chloride in here, an aqueous solution, the chloride ions are going to migrate in this direction to balance out the positive charge, and the potassium ions are going to migrate in this direction to balance out the negative charge. Okay? Now, again, if you're kind of curious, you probably noticed that there's also not a problem with this. There's no problem with this cell. Okay, we're able to harness the flow of electrons in the redox reaction. Everything's balanced. There's nothing wrong with this cell that's drawn on this slide. However, the cell is not going to operate in perpetuity, right? That's just a fancy way of me saying it's not going to run forever, is it? Because eventually the zinc bar is going to deteriorate. Eventually you're going to run out of ions in solution. Eventually the salt bridge is going to wear out, right? You don't have an infinite number of chloride and potassium ions in there. But it is a functioning electrochemical cell where we can produce a voltage. So I want you to give me a thumbs up if you understand the rationale as to how we got from a spontaneous reaction between zinc and copper 2+ ions. We said we can separate those into two separate beakers to harness the flow of electrons, but in order to balance out the charges that would be formed in this electrochemical cell, we have to complete it with a salt bridge, and now we have a complete electrochemical cell where we can harness the flow of electrons. Give me a thumbs up if you follow me even part of the way on this. Is anybody with me here? Maybe I need to, yeah. Okay, thanks, Joey. Thanks, Katie. Violet, gang, great. Okay, that's an electrochemical cell. And you're thinking, well, that's just like if I was to go to the store and buy a D battery or a C battery or a AA battery and put it in my remote control or whatever, it's, same kind of thing. There's a chemical reaction that takes place there that generates electricity, but it doesn't last forever. It wears out over time. And a battery is based off of this principle. It's harnessing the power of a redox reaction. And so you've got to be able to understand an electrochemical cell, but you can imagine that you can see that there's a lot involved in just drawing out an electrochemical cell. You got to draw beakers and U-tubes and voltmeters and all this stuff. And we're going to take a look at drawing an electrochemical cell later. I'll, try to harness my best artistic prowess to do that. But this electrochemical cell that's on this slide here, there's a way that we can write it a shorthand for this electrochemical cell, and we call that shorthand line notation. And you need to know how to represent line notation. Now, before I move on, my students love shortcuts or mnemonics, little tricks that I can give them to memorize things along the way. And something that I want you to memorize, it's going to be very helpful, is an ox and red cat. Okay. Now, again, if you read the textbook and the slides before coming to class, you can figure out where I'm going. And this is simply a shorthand to help us remember that where oxidation occurs, that is at the anode, what's called the anode, and where reduction occurs, that is at the cathode. So see if you can memorize that, an ox and red cat. So let's get back to the line notation, and I'm going to refer to an ox and red cat several times throughout today's lecture. Here we have that line notation representing that electrochemical cell. Here on the, or in the middle, we can think of this double line here as representing the salt bridge. So this is our salt bridge represented here. So we have one half of the cell over here, and we have the other half of the cell over here, right? Because on the left-hand side, I had my zinc in my solution of zinc 2+. And on the right-hand side, I had my copper in my solution of copper 2+. So the way that we represent things is that we put the reactant first, right? Our reactant was the zinc. The product after the redox reaction occurs is the zinc 2+, and the same thing occurs on the other side, right? The reactant was the copper 2+, and the product was the solid copper that was deposited. This is our product. Okay, so we write them in that order. We have to include their states of matter. What are the possible states of matter? Solid, liquid, gas, or aqueous solution. Since the solid zinc and solid copper are solids, we put S after them. But for the ions, the zinc 2+ ion and the copper 2+ ion, we write out not only their state of matter, that they are aqueous, but we also write out their concentrations. Okay, we put in their concentrations. You can see that each solution was a 1 molar solution. Now, there's one more thing that I haven't addressed in the line notation, and that is the single lines that divide the zinc and the zinc 2+ ion and the copper 2+ and the solid copper. Well, these lines here represent the anode and the cathode. If the zinc is undergoing oxidation, remember I told you to remember that we have an-ox. And so this line here, I'm trying to get my green pen, this line here represents the anode, and this line here represents the cathode. Again, I'll repeat that. Remember, we had an-ox and red cat. So since this is oxidation, when zinc goes from solid zinc to zinc 2+, that is the anode. And since the copper 2+ ions are being reduced, undergoing reduction, we have red cat, and so that is our cathode. Okay, that vertical line, again, the anode and the cathode, is really just the phase boundary between the electrode and the electrolyte, right? The electrode is just the solid piece of metal, whether it be copper or zinc, and the electrolyte is the ionic solution, whether it's zinc 2 sulfate or copper 2 sulfate. Again, the double vertical line represents the separation between the electrode compartments. Another way of stating that would be to say it represents the salt bridge. By convention, we always put the anode on the left. So this is something you can just memorize along the way. Anode is going to be on the left, and the cathode is always written on the right. And we always put the reactants for products. I'm not going to highlight that because my students are usually solid on, yeah, I should put reactants before I put products. Okay, now here's where it's going to get interesting today. If you have a spontaneous redox reaction, and so far we've only looked at spontaneous redox reactions, it can serve as a source of electrical energy. So what are we doing? We're making electrical energy, or we're harnessing, I should say, electrical energy by using this galvanic cell. We're taking advantage of a spontaneous redox reaction. Now, what about a case where you're using, where you are looking at a redox reaction and you have no material that can serve as a solid electrode? Like, say, for example, you don't have solid zinc or solid copper. What do you do in that kind of case? And if you're wondering, what kind of case would that be? Well, that would be a very good question. So I put in an example, and this is an example that comes straight out of the OpenStax textbook. Let's say you had this redox reaction here, where magnesium is undergoing oxidation to magnesium 2+, but iron 3+ is not being reduced to iron solid or solid iron. It's undergoing reduction, yeah, but it's just undergoing reduction to another ion. So we don't have a solid piece of iron in here anywhere. So what the heck do you do in this kind of situation? Well, in that kind of situation, for your electrode where you don't have any solid, you would use an inert metal. And the common inert metal that's used is platinum, right? Platinum is a valuable metal because it is inert, okay? It's unreactive. And so let's say you had this reaction and you wanted to set up a galvanic cell, again, for this reaction shown right here. Magnesium is a solid, and we could easily have a magnesium anode, no problem. Instead of a bar, if you're like, what the heck is this? Okay, they just have a coil of metal, right? Magnesium is a very, when you have a small enough strip, it's going to be, you're going to be able to shape that and bend it. And so since we don't have iron to put over here, we don't have solid iron as part of our electrochemical cell, you use platinum. And so as the magnesium becomes oxidized, the magnesium is going to lose 2 electrons, right, which will flow through the wire. They're going to come down through the platinum, and the reduction of the iron 3 plus actually occurs at the surface of the platinum electrode. So the electrons are going to flow through here, if you will, and then the electron is going to be, grabbed at the surface and is going to reduce the iron 3 to iron 2. Now, again, if you took the time to read the textbook, you'd know that a platinum electrode is also used in the standard hydrogen electrode, which we're going to talk about in a couple of seconds. When you use an inert metal like platinum as an electrode, we call it an inactive electrode. Whenever you have an electrode that's made out of a metal that's part of the cell, though, that's involved in the redox reaction, we call those active electrodes. So active and inactive electrode, it's a term. It comes up in the book, I think, maybe once, okay? Again, how would you write out a line diagram, or how would you represent the line notation? So this is the line notation for this electrochemical cell. It's going to be a little different, isn't it? Some things are the same, right? Over here we have this is our anode on this side, okay? Over here we have our cathode. And I know that on the last electrochemical cell, I just said, this is your anode, this is your cathode. You can think about the whole side as being the anode, the whole side as being the cathode, right? Because we have an, ox, and red, chem, right? At the anode, what's happening? Oxidation. The magnesium is going from magnesium 0 to magnesium 2 plus. So it's losing electrons. What's happening here is that the iron is being reduced from iron 3 plus, 3 plus to iron 2 plus. But what we have to do that's a little bit different on the right-hand side of the salt bridge here is we list the concentrations of the solutions. We have iron 3 chloride and iron 2 chloride. Here we have both of their concentrations, so we put those in here. But then the interface between the aqueous and solid phase is represented by this line here, and then we put the platinum or the inert metal on the end like that. Okay, so that represents the electrode, or the where the reduction is occurring, where the electrons are flowing through. And then this line here represents the phase boundary. So our phase boundary. All right, there we go. And, our book goes into a little bit of detail about this. I don't know if they ask a ton of questions about these, but it's something that I want you to be aware of, okay? Because it's not uncommon to structure a galvanic cell where you have an inert electrode as part of the system. So really, one of the major take-home messages here is that you would include the platinum at the end like this. And of course, you include all your states of matter. And of course, what's the best way to get proficient at writing out line notation? Practice it. Really, it's the best way to master it. It's the way that, all students who have come before you, that's the way they mastered it. Well, with that in mind, let's try drawing a galvanic cell. Now, I'm not, obviously, on your exam, if it's multiple choice, I'm not going to ask you to draw a galvanic cell. But what's great about trying to draw a galvanic cell is that it really kind of demonstrates to you whether you're capable of connecting all the dots, if you will, if you can connect all the concepts together. So let's see if we can draw a galvanic cell. God help me with my artistic abilities here that show the redox reaction that's represented here in this equation. And then it says also draw out the line notation. So it's kind of a two-part question here. So what do we need to do? We're going to start by drawing a couple of beakers. Right? We need a couple of beakers. that we can put in both of our solutions. Sorry, I'm having a problem here with my computer. There we go. Okay, so let's draw a couple of beakers. So we're going to have a beaker over here, and we're going to have a beaker over here. And in both of those beakers, we're going to have our two solutions. Now, what's happening here? The copper is going from copper 0 to copper 2 plus, and my silver is going from silver with a +1 charge to silver 0. And so the silver is undergoing reduction. The copper is undergoing oxidation. We had an ox and red cat. So remember, we put the anode on the left and we put the cathode on the right. So if the anode is where the oxidation is occurring, what am I going to have in my anode? I'm going to have my solution, which is going to contain copper 2 nitrate. So I could just write out copper 2 nitrate, but I'm going to show copper 2 plus ions, and I'm going to have nitrate ions. So I'll just write NO3 minus, and I'm also going to have my copper bar submerged in here. So this is copper, that is a solid. I'll try and color that in a little bit here. So there's my copper bar. Before I put in the voltmeter and my salt bridge, I'm going to draw the other electrode. So I've got my cathode. In my cathode, I'm going to have a solution of silver nitrate. So silver ions that are going to be aqueous, nitrate ions that are going to be aqueous. I have my bar of silver. I should have put it more like that. So this is my silver. It is also a solid. So there's my silver, like that. I'm going to have my two electrodes connected by a wire to my voltmeter. I'll just put a dial on it like that. Okay, like that. But I'm missing something. Okay, I know that electrons are spontaneously going to flow because they're telling me here that this is a spontaneous reaction. I know that electrons are going to flow through the wire, right, in this direction. I'm going to have electrons flowing so that the copper is getting oxidized and my silver is being reduced. But can anybody tell me what's missing here? There is a serious problem with my electrochemical cell, my galvanic cell. Anybody tell me what's missing? No? Yeah, thanks, Joel. Thanks, Shannon. Thanks, Jamil. Absolutely. It's the salt bridge. That's the main thing that's missing here. I see somebody says concentrations, but they don't tell us what the concentrations are here. I guess if it's a standard galvanic cell, you're right, the concentrations would be 1 molar, right? You'd be at 298 Kelvin and 1 atmosphere pressure. But yeah, the salt bridge, I'm going to put that in here. So let me try to draw a salt bridge in here. Make sure it's got to connect with the surface of the liquid, doesn't it? So I'll put my salt bridge. In my solutions, I think I literally just wrote salt bridge, okay? And that works. If you write, KCl, salt bridge or something like that. And since we're going to have a buildup of positive charge on the anode, we could say the chloride is going to be flowing in this direction. No, you can't see that, can you? That's my chloride. So we'll say chloride ions going in this direction, and then I'd have my potassium ions going in that direction. Anyhow, that's a pretty miserable looking thing. But anyhow, you get the idea. All right, now let's try and write out the line notation. And as my students pointed out, they said, yeah, you're missing the concentrations, Mr. Dion. I'll tell you what, since it's a standard galvanic cell, the concentrations are going to be 1.0 molar. But let's just include that in the line notation. So let's write out what the line notation is. I'll start by putting the double line for the salt bridge. I'm going to have my solid copper is my starting material. I end up with copper 2 plus ions. That's not nearly as much enough space, is it? So let me erase that. I've got my copper 2 plus ions. They are at a concentration of 1 molar. There's other, different ways you could write this out. Let me just clean this up. I'm kind of messy here with my writing today. Anyhow, we'll just put 1.0 molar like that. We'll put our salt bridge. Then we have our silver plus ions. So silver plus, it's aqueous. It's 1.0 molar. Then we have our phase boundary, and then we have our solid silver, like that. And there you have it. That's our line notation. Okay. Again, this is our anode over here. Again, you can think of this line as being the anode. I have it written in another slide like that too. You can think of this or this whole part as being the cathode. Sometimes I like to just think of this line as being the cathode. It is the phase boundary, but you can write it either way. And there you go. Give me a thumbs up if you think, I don't want to draw an electrochemical cell. I don't feel like doing that, but I think I could do line notation. Okay, that's the main thing. I want you to be able to represent, an electrochemical cell using line notation. I want you to all be confident at that, because you can see it'd be very easy for me to ask you a question about that. Well, here's the picture that's in our book that shows this same electrochemical cell. You can see that the salt bridge differs. Okay, all it has to be is an inert anion and cation, potassium chlorides, sodium nitrate. It doesn't matter. Okay, it's just got to be salts that aren't going to affect the pH of the solution. Anyhow, but this is their drawing, and you can see that, like my student pointed out, they put the concentration of the solution down here. So this is a more beautiful picture than what I drew. But anyhow, mine was good enough. So here's a summary of what we just talked about. Sometimes it's good to kind of take a step back and think about the 30,000-foot view of what we've seen so far. We spent some quality time talking about redox reactions. Seemed like my students were pretty good at that. And we spent quite a bit of time practicing balancing redox reactions in acid and base. But we saw today that if you compartmentalize or you separate the half reactions, you can harness the flow of electrons in a spontaneous redox reaction. One half cell has the anode. That is where oxidation occurs, right? The whole the whole an-ox thing. The other half cell is the cathode. And I told you we have red cat. Hopefully you won't forget that. Each half cell consists of an electrode that's in an aqueous solution. Notice that it didn't necessarily say an active electrode. It could be an inactive electrode. We join the half cells by a wire and a salt bridge, and there you go. We can harness the flow of electrons. Check this out. If you actually build a galvanic cell, which I have on this slide here, I thought I did. Son of a gun. I'm getting ahead of myself. I'm getting overly excited, but let me just show you this quickly, and then I'll back up. This is a real galvanic cell put together. So if you're like, does anybody ever do this? Yeah, absolutely. So this is a galvanic cell here that shows the reaction between zinc and copper 2+ ions. You can see that this is a copper bar. Where's my red pen? This is a copper, solid piece of copper. This is a solid piece of zinc. You can see the salt bridge. It's not very big. It's hard to see from the resolution, but there is a salt bridge in there. Anyhow, and then they hooked it up to a voltmeter, and you can see that they measured 1.10 volts. So I was overly excited, and I kind of skipped to that slide. I want to back up for a second here. So we're going to talk about what's called a cell potential in section 17.3. Now, in a circuit, like in a battery, the flow of charge, and it could be a circuit like in our galvanic cell, of course, the flow of charge, why does that occur, right? There's a spontaneous reaction. We all agreed on that it occurs, right? You can see the reaction occurring before your eyes when you take the zinc rod and you stuck it in a solution of copper 2 sulfate. But why does that happen? Okay, now we're going to answer that question. The big, why does this occur? It's because there's a difference in the electrical potential difference between the 2 points in the circuit. Put another way, you could say the two metals, the zinc and the copper, or the two ions, the zinc 2+ ion and the copper 2+ ion, they have different affinities for electrons. So the potential that we're going to measure, this electrical potential, reflects the driving force for a specific type of charge transfer process. Now here we're talking about the flow of electrons between reactants. And when we take a galvanic cell and we measure that potential difference, we call that a cell potential, which we call E cell, like that. Why do we get that flow? I'm answering the question for a second time. But the flow of the electrons in the galvanic cell is a result of the difference in electrical potentials at each electrode. Again, it's connected to the affinity of each metal and each ion for the electrons, right? There's got to be a tug of war for the electrons, if you will. And what we're going to spend some time doing now is looking at that tug of war. This is a slide that I skipped ahead to. I kind of borrowed this one a little bit from Dr. Diaz, who also teaches this class. I thought it was a nice picture. And that difference between the potential, or that difference in electrical potential, I should say, between the anode and the cathode, if you are the kind of person that likes to look around at other YouTube videos or the internet, or read other chemistry textbooks, you'll see it called several different things. Okay, you'll see it called cell voltage, the electromotive force. That's a big one that you'll see if you've ever read the textbook called CHEM. It's a very popular chemistry textbook. Electromotive force, cell potential, E cell is what we're going to call it most of the time. And there is a difference between E cell and E naught cell that we're going to get into. So let's get back to this electrochemical cell and let's talk about this cell potential, right? The amount of voltage that is produced when we build this galvanic cell. Here's the redox reaction, nothing new there. Here's the concentrations of our ions. They are both 1 molar, so this is a standard galvanic cell. The temperature is 298 Kelvin or 25 degrees Celsius. The atmospheric pressure is around 1 atm or 1 bar. Here is our line notation, so nothing new there. Let's get into this voltage though. But before we can get into the voltage of the galvanic cell that shows the reaction between the copper and zinc, we have to talk about standard reduction potential. Okay, everybody knows what reduction is at this point, right? Reduction is gaining electrons. Gaining electrons reduced, right? GER, or what do we like here more? RIG, right? Reduction is gaining electrons. So how do we measure how much a metal or an ion or a polyatomic ion wants to gain electrons? Well, we call it its standard reduction potential. It's the amount of voltage associated with the reduction reaction at an electrode when all solutes are 1 molar and all gases are 1 atmosphere. But the thing is, we have to have a reference point where we can, a reference point by which we can measure standard reduction potentials. We have to have some kind of reference point. Now, just like when we measure the height of Pikes Peak, we say it's, it's approximately 13,000 something, or no, it's not a 13er, is it? Or if it's not a 14er, sorry. Okay, so anyhow, it's 13,000 something feet relative to what? Well, it's not relative to the bottom of the ocean, it's relative to sea level. So just like we use sea level, in order to simplify the collection and sharing of data for half reactions, the scientific community has assigned what we call the standard hydrogen electrode as a reference point, giving it a standard reduction potential of 0 volts. So here is a standard hydrogen electrode. The way that we make a standard hydrogen electrode is that we have a 1 molar solution of hydrochloric acid in which we submerge a platinum electrode. Now remember, platinum is a relatively inert metal. It is unreactive. We have in the 1 molar solution of HCl, we're going to have a 1 molar solution of H plus ions and Cl minus ions. So we've got 1 molar H plus ions, and we also bubble H2 gas or hydrogen gas at an atmosphere of at a pressure of 1 atmosphere. And so if we observe the reduction of a proton, right, a hydrogen ion, which is a proton with a concentration of 1 molar, when that hydrogen ion or that proton gets reduced, we have the reduction equation shown right here. We have 2 protons plus 2 electrons gives you a hydrogen, H2. Again, we assign this reduction reaction a value of 0 volts. So we say its standard reduction potential is 0 volts. So again, when we measure half reactions for other elements and ions, they are recorded with respect to the standard hydrogen electrode. This is just another figure showing a standard hydrogen electrode. It comes from your textbook, but I want to get into it in a little bit more detail. So again, we're going to measure the electrical potential of a half reaction by referencing it to the standard hydrogen electrode. So here we have a zinc bar submerged in a 1 molar solution of zinc sulfate. So standard conditions, we're going to assume this is at 298 Kelvin. We're going to assume that the pressure is 1 atmosphere or nearly 1 bar. So we'll put T is equal to 298 Kelvin. The pressure is 1 atmosphere. And again, this is standard conditions. Concentration of everything is 1 molar. What happens when we put the zinc bar in the zinc sulfate solution, and on the other side of our galvanic cell, we have the standard hydrogen electrode, right? This is the standard hydrogen electrode, which we sometimes call the SHE. Well, what happens is that we see a voltage of 0.76 volts, which is the measurement of the flow of electrons. Now, who's being oxidized here? The flow of electrons is going from the zinc through the platinum wire to the solution of 1 molar HCl. So the zinc is being oxidized, and the protons in the 1 molar HCl solution are being reduced. So we have our anode, which is where the oxidation occurs, and we have our cathode, which is where the reduction occurs. You can see that I also put the line notation here. Again, on this side, we put our anode. On this side, we put our cathode. Notice that there's a phase boundary here because we have our platinum electrode as well. Well, we have another phase boundary here because it's the phase boundary between an aqueous solution in gas. So anyhow, there's 2 phase boundaries there, if you will. But anyhow, when we add these 2 half reactions, right, these are both half reactions. When we add them together, what happens? The 2 electrons cancel out, and we get this net ionic equation here. The zinc is being oxidized to zinc 2 plus, and the protons that come from the 1 molar solution of HCl are being reduced to hydrogen. Now again, we assign the standard hydrogen electrode, we say that its cell potential, and this is a standard cell potential, or sorry, standard reduction potential, is being 0 volts. Okay, well, let me show you a formula that's going to be very important for you moving forward. And that's that the standard cell potential, which is this here, which we sometimes call the standard electromotive force. So the standard cell potential is equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. Note, and you know, I've taught this before, so I know enough to point out that both of these, both are standard reduction potentials. Okay, sometimes I'll have students mix these up. Don't believe me? Go back in my slides here. And I said that the E naught, okay, the E naught is the standard reduction potential is associated with a reduction reaction. And we're going to look at a table that has standard reduction potentials in a minute. And if you read the textbook, you know where I'm going with this. But again, when we use this formula, which you're going to need for your next exam, the E cell, the standard potential of the cell is equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. So we have the standard potential of our cell was equal to 0.76 volts, which equals to the standard reduction potential of, in this case, the standard hydrogen electrode, which is the cathode. It is where reduction occurs. Subtract the standard reduction potential of zinc 2 plus, right? We know, now this is where I really don't want you to mess up. I know that the zinc is being converted to zinc 2 plus, okay? But remember, this represents a standard reduction potential, even though the zinc is getting oxidized, okay? So don't mix up the 2 here. You just take the value from the table when we get there in a second. Okay, so we have 0.76 volts being equal to 0, subtract the standard reduction potential of the zinc 2 plus to zinc. So that means that the standard reduction potential of zinc 2 plus to zinc is equal to negative 0.76 volts. Here's the standard reduction reaction of zinc 2 plus. We have zinc 2 plus being reduced by 2 electrons to give us solid zinc, and we get that our standard reduction potential is negative 0.76 volts. I know I probably over-explained that a little bit, but give me a thumbs up if you're with me so far, and just on the idea of this formula, because obviously we're going to use it, okay? You know, it's like anything in life. Until you start to use a formula, it's really hard to become familiarized with it and really have it ingrained in your memory or in your, in your tool bag or whatever. Anyhow, so we just looked at an example where the standard hydrogen electrode was the cathode. Right here, the SHE is the cathode. What if I had the standard hydrogen electrode as an anode? Here's an example that shows just that. Here we have the standard hydrogen electrode, which is the anode in this case. This is where oxidation is occurring. What's the oxidation reaction? Now the hydrogen gas that's being bubbled in here is going to get oxidized to H plus ions, right? Plus electrons. Those electrons are going to flow through the wire in this direction. So I have the electrons flowing in this direction. And what's going to happen? They're going to reduce the copper 2 plus ions. Same old formula that we looked at on the last slide. Look, we have E cell, standard potential of the cell, is equal to the standard reduction potential of the cathode minus the standard reduction potential of the anode. So we have 0.34 is equal to the standard reduction potential of copper 2 plus minus 0 volts, and we get the standard reduction potential of copper 2 plus is equal to 0.34 volts. Well, if we compare that to what we saw in the last slide, if we saw versus the standard reduction potential of zinc 2 plus to zinc, which was negative 0.76 volts. If you're kind of asleep or not following me 100% here, just follow me for 1 minute here. You see these two values for the standard reduction potential of these two ions? Well, the copper 2 plus has a positive standard reduction potential, and the zinc has a negative standard reduction potential. The more positive the standard reduction potential is, the hungrier the ion is for electrons. So what I'm saying is that copper 2 plus has a greater hunger or thirst or desire or, for electrons. It's going to grab those electrons with a greater force or a greater ability than the zinc 2 plus will. If you're wondering, what about other ions and molecules and atoms, Mr. Dion? Could I find them in a table? Yes. Now, this is a table that comes from another book. Okay, but I just want to show you quickly here. I have all of these half reactions, and these are all standard reduction potentials. You can see that fluorine has the greatest standard reduction potential. That means that fluorine is super duper hungry for electrons. It's got a standard reduction potential of positive 2.87 volts. If you go down to the bottom, you're like, what's on the bottom, Mr. Dion? Well, lithium. A lithium cation is way down here on the bottom. Okay. A lithium cation, you think about group 1A elements, they're pretty happy being positive ions, aren't they? But if lithium loses one electron, it becomes isoelectronic with helium. So a lithium cation has a very low hunger for electrons. Okay, and then we have our standard hydrogen electrode, which is somewhere in the middle. That's our baseline. Everything is measured off of that. Now, in our textbook, it also has a table of standard reduction potentials. It's a little different than this one. I thought this one was a really good one, though, for teaching purposes. Yeah, I took it from another book because I thought it was really good for teaching purposes. Now, see if you can just follow along with me through these few bullet points here. So the E naught is a standard what potential? Reduction potential. Don't start thinking this anything. These equations all show reductions. Don't believe me? Look at them. They're all adding electrons. The entire thing is adding electrons. gains electrons reduced, reduction is gaining, however you want to think about it. So all of these voltages are a measurement of standard reduction potentials. The more positive the standard reduction potential, the greater tendency for the substance to be reduced. That's a fancier way of saying the hungrier it is for electrons. These half-cell reactions are reversible. Okay, they are reversible, but if you want to switch them, if you want to flip them around, you'd have to flip the sign of the standard reduction potential. You'd have to flip a negative to a positive. Oh, that's not what I meant to do. A negative to a positive or a positive to a negative. Now here's a cool rule. It says any species on the left will spontaneously react with all of the species that are below it and to the right. And that's what we call the diagonal rule. Remember the reaction that we saw between zinc, solid zinc, and copper 2+ ions? Check this out. Now, I need a new prescription here pretty bad. But if we find zinc, where's my zinc? It was what, 0.3? No, that was the copper 2+. Yeah, here's my zinc. There we go. And here's my copper 2+. So here's the diagonal rule, like that. Let's follow it again. It says, son of a gun, didn't mean to do that. A species on the left will spontaneously react with the species below it and to the right. We know that the copper 2+ ions react spontaneously with the solid zinc. I thought there was another example here that they brought up in the textbook. So if you're an avid reader of the textbook, there's another example that they brought up in the textbook, which I think was silver and lead. I think that's one of the ones they used to kind of explain the whole idea of calculating the cell potential. So, for example, silver ions and will oxidize, lead. So you can see that since fluorine is the king of the castle, right? Fluorine is really happy to be reduced. That means fluorine is going to oxidize anything. So fluorine is like a super strong oxidizing agent. In fact, it's the strongest one on this table. Anyhow, another thing, and this goes against a lot of the things you've learned in chemistry class, is if you change the stoichiometric coefficient of a half-cell reaction, it doesn't change the value of E. And if you're like, what do you mean by that, Mr. Dion? If you take, for example, this reaction here, zinc being reduced to solid zinc, if you were to multiply this reaction by 2, this would be unaffected. Okay, it doesn't affect that. There we go. All right, let's move on from there. There's one more thing I wanted to tell you. Oh yeah, that's this. Okay, I added one more note on this. That the standard, or the E naught of the cell, the standard potential of the cell is going to be equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. So remember that the standard reduction potential of anode or cathode is a measurement of how hungry it is for electrons. So if I put a cathode that has a really big positive number here, and I subtract something that's a really weak, has a really weak hunger for electrons, it's going to have a negative value, right? Let's say you react fluorine with something way the hell down here, like, I don't know, potassium. Okay, you're going to have a positive subtract a negative number. So that means your E cell would be positive, right? If you've got a spontaneous reaction, then it follows that your E cell should be a positive number. Here is the table of standard reduction potentials from our textbook. I don't know why they have so many sig figs for some of these. There's got to be a rationale to it. I haven't been able to figure it out yet because usually they only report them to the hundredths place. Again, I'm not sure what the connection is, why you need to have, 5 sig figs here. I don't get it, but again, there's might be something there that I'm not following. But here's the table from your book that you'll probably use most of the time. And if you're wondering, could I use this table? Sure, you can use that one. I put it in the slide so you can use that one to solve any problems. All right. So to summarize, the half-cell potential, so all those standard reduction potential values from that table all came from pairing each one of those ions or atoms with the standard hydrogen electrode and measuring the cell's potential. Let's see here. You've got to have consistency for the half cell. So you have to have standard conditions, 1 molar solutions. You can't change the temperature. It's got to be room temperature, 298 Kelvin, 1 atmosphere of pressure. If you reverse the sign, E naught changes. And yeah, I told you that the strongest oxidizing agents have large standard reduction potentials, and strong reducing agents, of course, are going to have low standard reduction potentials. All right, that's a lot of talking. Let's take a look at some examples here. And we'll start it with 6A. And you could use the table that's in our textbook, the appendix, to solve these problems, or you can use that other one that I put in the book, or in the slides rather, which is, I think, an easier one to refer to. But let's take a look here. It says calculate the standard cell potential, E cell, from the standard reduction values in the standard reduction potentials table provided in the appendix. I'm going to use the other table just because it's easier, I find, for the following galvanic cells. Write a balanced equation for each cell reaction. So for the first one, I'll go back and refer to it. So we've got copper 2 plus and zinc 2 plus. So let's go back to the table, back to the Shack Jack. So we've got copper 2 plus, which was here. Maybe I should delete some of this spinach. Okay, so we've got copper 2 plus, which is here. And we've got zinc, which is right here. And then we have their standard reduction potential. So I'm just going to rewrite that information over here on this slide. So let's write down the reduction reactions. We have the copper 2 plus 2 electrons gives you solid copper. The standard reduction potential of copper 2 plus to copper is equal to positive 0.34 volts. When we reduce zinc 2 plus ions to solid zinc, the standard reduction potential, remember it's reduction, so it's zinc 2 plus to zinc, is negative 0.76 volts. Now, we want to produce a functioning galvanic cell here. So since the standard reduction potential is larger here, this will be our cathode. This will be our cathode. And now we're going to use our formula that the standard cell potential is equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. So I get 0.34 volts, subtract negative 0.76 volts, and I get that the standard cell potential is equal to 1.10 volts, like that. Then it says, write a balanced equation for each cell reaction. So we've written out the half reaction, but we know that the cell reaction is the sum of this half reaction, because the copper is being reduced, right? Because the copper is the cathode, red cat, but it's going to be the reverse of this reaction. So let's write it down. We have our, I'll just copy this to make it easier. So we have copy, and we're going to paste this in here. There's our reduction. Our oxidation is going to be and then we're going to add those two together. The electrons are going to cancel, and we end up with our balanced equation, which is zinc in the solid phase plus copper 2 ions in the aqueous phase produces zinc ions plus solid copper, like that. Okay, again, we want to produce a functioning electrochemical cell. I don't think I gave myself any more space to solve this one, so I'm going to skip B and C for now. If we have time later on, we'll come back to them. Let's take a look at question number 7. This is a really classic question. I don't think it's that much of a stretch for my students. It says, will the following reaction be spontaneous, yes or no? All we have to do is calculate E cell. I told you that the standard potential of the cell, which is equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. If E cell is positive, reaction is spontaneous. And if E cell is negative, reaction is non-spontaneous. Non-spontaneous, like that. Okay, so what's the cathode and what's the anode? Let's take a look. I have my iron being oxidized, so this must be my anode. And I have my manganese being reduced, so this must be my cathode. Now I look up the standard reduction potentials for both of these. So for my cathode, I'm not going to refer back to the table. I just looked up the values. I have manganese 2 plus 2 electrons. Remember standard reduction. We get manganese. The standard reduction potential is negative 1.185 volts. I must have taken this from our appendix. For the anode, we have iron 2 plus 1 standard reduction potential should be written the other way around. Let's go back to the table here. So for iron 3 plus to iron 2 plus, is that in this table here? See, this is a mistake here in this slide, isn't it? Because this should say iron 2 plus. So we have this 0.771 volts. So let's go back and write that down. So we have iron 3 plus an electron, giving you iron 2 plus. We have the E for that is being 0.771 volts. So we have our E cell, our standard cell potential, is being equal to negative 1.185 volts. Subtract 0.771 volts. You can see right away that the E cell is going to be negative. It gives you negative 1.96 volts. Okay, and so the reaction will be non-spontaneous. So E cell standard cell potential is negative, therefore non-spontaneous. Non-spontaneous, like that. There we go. Give me a thumbs up if you follow me on that one. That I would guarantee I will ask on your next exam. Something pretty much like it, where you just have to, all you had to do here is use this formula and calculate the standard cell potential. If it's positive, it's spontaneous. If it's negative, it's non-spontaneous. Sorry, guys, I'm having a hard time concentrating. Both of my next door neighbors approached me a couple of weeks ago because they are both getting their driveways redone. So they said, hey, do you want to get your driveway redone? And they just started jackhammering. It's Monday morning. They just started jackhammering both of their driveways, and it's very loud. Anyhow, it's kind of funny, but kind of not. Anyhow, okay, where was I? Determine which of the following is a stronger oxidizing agent. Again, all you got to do is go to the table. Remember that the greater standard reduction potential, okay, equals stronger oxidizing agent. Like that. You know, I'll just write these down for you. So for A, if you look at the reduction of bromine, so we have Br2 plus 2 electrons gives you 2 bromide ions. The standard reduction potential is plus 1.07 volts. If you look at the reduction of gold 3 plus 3 electrons to produce solid gold, you get a standard reduction potential of positive 1.50 volts. Here's my question to you. Which one is a stronger oxidizing agent, bromine or gold 3 plus? It is not a trick question. Yeah, Jamil, it's just the one with the higher voltage. That's it. That's all there is to it. So the answer is gold 3 plus. Let's try another one. Let's look. Don't believe me? So we got bromine and gold. Let's go back all the way up here to the table. The one that shows all of them. You know, I think I didn't even put it in here after. I thought it, yeah, there we go. So we're comparing bromine and gold. So we have gold, which was what? Up here. So you have gold 3 plus. I know it's a little grainy, but you can see here, this is gold 3 plus. There we go. That's gold 3 plus. And bromine is down here. Bromine is lower, therefore stronger. Done. Let's skip all the way ahead to D. It's oxygen in acid media versus oxygen in basic media. Look, if you have oxygen, this is in acid. How do I know that? H plus. This is oxygen in basic media. How do I know? Hydroxide. This one's plus 0.68. This one's plus 0.4. Which one's going to be stronger? If I go back here, will it be the oxygen in acid or the oxygen in base? And it's not a trick question. Based off of those numbers. Yeah. The 0.68. So it's going to be the oxygen in acid. Okay, that's it. It's just looking at the table of standard reduction potentials, which I've probably spent too much time on because we're running out of time here. But let's switch gears. We really only have 2 sections left because in the interest of time, I'm going to skip sections 17.5 and 17.6. I know that sounds probably like music to your ears. We're going to skip the sections on batteries and corrosion. The reason why is I'm not going to ask any questions on your exam about them, and there will be no questions on your final exam about them. There's no questions on the ACS about those 2 topics. So just in the interest of time, we'll skip them. Anyhow, where was I? We got 3.5 hours left, so I just want to spend a little bit of time with you talking about section 17.4. I want to slow down a little bit and discuss cell potential, free energy, and equilibrium, right? We spent a lot of time looking at delta G. We spent a lot of time looking at equilibrium. And now we're going to connect it to cell potential, E. Okay? So let's take a look here. It says, if calculated, the standard cell potential of a redox reaction is positive, then the reaction is spontaneous. Yeah, we figured that out. So that's why if you have a galvanic cell, which is a cell that produces a current, the E cell is always going to be a positive number. Okay, always going to be a positive number. If E cell is negative, reaction's non-spontaneous. So all you need to know here, E cell positive, spontaneous reaction, E cell negative, non-spontaneous reaction, which we've already gone over. So now we want to take it a step further and connect it to delta G and equilibrium constant. Because delta G was a measure of spontaneity too, wasn't it? We said that since delta G was equal to negative T times delta S, that a negative delta G was a spontaneous reaction. When we took a look at equilibrium constants all through the beginning of the course, chapters 12, 13, 14, we said that when K is greater than 1, we have a spontaneous reaction, right? We have more products than we do reactants. What was delta G? What is free energy? Now, that is something that I really just referred to very briefly. And in fact, our book doesn't go into a whole, pile of information about what delta G is. But if you read the previous chapter that dealt with free energy, it said that free energy, the standard change in free energy, was basically the maximum amount of work that could be harnessed by a system. Okay? Now, if we have a galvanic cell and it's under standard state conditions, the work is associated with the transfer of those electrons. And so we could say that the standard change in free energy, or the change in standard free energy, is equal to the maximum amount of work that we can get from those electrons. Well, let's take that a little bit further. If our change in free energy, standard free energy, is equal to the maximum amount of work that we could get from those electrons, we say that it's equal to negative N times F times the standard cell potential. You know what standard cell potential is, don't you? We've taken a look at that. But you're probably unsure, if you haven't read the book, as to what N and F are. So let's go over it here. Remember that the not, right, this little symbol represents not, N-A-U-G-H-T, not. It's not. Okay, it's not. Anyhow, not indicates standard conditions. We've talked about those. For a gas, it's 1 atmosphere or 1 bar. If we have an aqueous solution, it's 1 molar. Okay. Delta G is standard free energy change. Okay, good. Delta G values of formation listed in our appendix are at 298 Kelvin. But anyhow, E cell is our standard cell potential. We've calculated that, or we've looked at how to calculate that today. Standard cell potential is equal to the standard reduction potential of the cathode, subtract the standard reduction potential of the anode. So here you go. N, if you're wondering what N is the number of moles of electrons that are transferred in a balanced redox reaction. So remember how when we look at, two electrons flowing or 1 electron flowing, or if you had gold 3+ being reduced, it's 3 electrons. Well, the number of electrons that are transferred in the redox process, that's N. So we've looked at that piles of times already, so you know how to calculate N. F is the Faraday constant. Of course, I'm going to give you the Faraday constant, which is 96,480 joules per mole times volts. Okay, and we'll talk about that probably even more during the next lecture. But notice that delta G and E have opposite signs. And you're like, well, that makes sense because you told me, Mr. Dion, that if E cell is positive, I have a spontaneous reaction. If my F is a positive number, my N is a positive number. If I take a positive and I multiply it by a negative, I get a negative. And when delta G is negative, my reaction is spontaneous. So it makes sense. When my delta G is negative, my E cell is going to be positive. They have opposite signs from one another. Well, what happens in a redox reaction, just like when we took reactions and we examined them from the point of view of standard free energy changes or the equilibrium constant, reactions are going to reach a state of equilibrium. And you're going to see this equation come up a lot in this class, that the standard cell potential is equal to R, the gas constant, multiplied by temperature, divided by the number of electrons transferred, multiplied by Faraday's constant. Well, let me show you a treatment of how we get this reaction here and how we can have a simplified form and how we can have more than one simplified form, because a student actually sent me an email about this. Let me show you something kind of quickly here. If we start on the top left and we say that the change in free energy is equal to the negative of the number of electrons transferred in our redox reaction multiplied by Faraday's constant. Here I have it to only 3 sig figs, which is usually good enough for everything we do. 96,500 joules per moles times volts. Since a joule per volt is equal to a coulomb, you can also write it as 96,500 coulombs per volt. Either one is fine. Well, what if we're in standard conditions, right? This equation represents non-standard conditions, but what if we're in standard conditions? At standard conditions, the standard free energy change is going to be equal to N times F times the standard cell potential. Well, do you guys remember that delta G naught is equal to negative RT ln K? So why can't I say that negative RT ln of K, which is an equation we looked at before in this class, is equal to negative N times Faraday's constant times the standard cell potential? So now I can rearrange this formula that I have in the blue box and I can solve for standard cell potential. And I get the formula that was on the previous slide, this formula right here. Now, when I plug in the numbers for R, which is a constant, Faraday's constant, which is a constant, and temperature, which we're going to perform or have our galvanic cell set up at 298 Kelvin, I can simplify it to E cell is equal to 0.0257 volts divided by N multiplied by the natural logarithm of the equilibrium constant. You could also write this equation as E naught cell is equal to 0.0592 volts divided by the number of electrons multiplied by the log of the equilibrium constant. Notice that I have two different numbers here, but I have the natural log and the log to base 10. The reason I put both of these equations on here is a good one. It's because you see both of these equations in textbooks and the internet in about a 50-50 ratio. That means if you're kind of perusing the internet and trying to learn more about standard cell potentials, you're going to see either one of these equations depending on the situation. I am not going to go through the derivation of where, how you get from here to here. But in order to solve for it, if you want to take the time to do it, which only takes a second, but you should know that the natural logarithm of x is equal to the log to the base e of x. And from that, you can solve and go from here to here. Again, usually when I teach this class, I think I use this one more. I use the natural logarithm because that's what we start out with here, right? And it's what we start out with here. Okay, but again, you're going to see both. Give me a thumbs up if you just follow me on that concept. You're going to see both. Some of you have probably already noticed that both show up if you looked anywhere else besides our textbook or just looked around. You've probably seen both. Okay, cool. Because I did have a student write me an email and say, why these equations look pretty similar to me. Well, they're not, but they'll give you the same answer. But what have we got from this slide? Now we have a relationship between equilibrium constant, E cell, and standard free energy change. To summarize right here, okay, I'm going to skip ahead to this. You guys know free energy change. I'm sure you all have that memorized by now. I know I don't have a lot of time, but follow me here. Look, when delta G is negative, you got a spontaneous reaction. E cell is going to be positive. Come on, you guys remember, equilibrium constant when it's greater than 1, I've got a reaction that's going to have more products. So it's spontaneous, right? More products at equilibrium. What if my delta G is greater than 0? Hey, that's a non-spontaneous reaction, man. My E cell is going to be negative, and my equilibrium constant is going to be less than 1. I'm going to have mostly reactants. It's very rare, but if you did have a scenario where your standard free energy change is 0, well, then your standard cell potential is going to be 0, and your equilibrium constant would be exactly 1. All right, that's kind of where I wanted to get to today. Yeah, you can see that from this equation that the more positive E is, then K is going to be greater than 1. And when K is less than 1, you're going to have an E that is negative, right? Because the natural logarithm of a number greater than 1 is a positive number, and the natural logarithm of a number less than 1 is negative. So it's kind of beautiful how it all ties together. And yeah, there we go. And that's really what I wanted to get to. And what we're going to do next class is we're going to start by taking a look at question 17.6, which deals with something, a reaction at standard conditions. And then we're going to deviate or move away from standard conditions and talk about when we have reactions where everything isn't in their standard states. What did I do there? There we go. And we're going to take a look at the Nernst equation. So next class, we're going to take a look at the Nernst equation and concentration cells very quickly. And we're going to skip section 17.5, 17.6. And then the last thing we'll deal with is electrolysis. Stop recording.